All right, class. Um, Sorry. Let's continue from where we left last time. I want to give a very basic example, eh, which I think it's appearing in the problem set, but I think let me just put it on the board. You've got water here acting like a base. It's subtracting a hydrogen from hydrogen bromide, and it's giving protonated, hydroxonium ion plus uh, bromide ion. Now, this is the standard mechanism. Now, when it is like this one, it can be a bit challenging because sometimes people say, hey, just put an arrow like this one, but so this is just the normal curly arrow illustration. Now, want to combine this curly arrow illustration. No, but by the way, I think as I mentioned earlier, when an atom has got a lone pair, or maybe it's got a double bond, it's good to show exactly where the electrons are starting from. In this case, if an atom has got two lone pairs, please show all the lone pairs. In this case, bromine has got three lone pairs in this structure. So when this bond is going to be breaking, it's going to be adding an extra lone pair. So that in this case, it is going to be having four lone pairs. Now in this case, this illustration here, because I want to show it horizontal here, I've just twisted this molecule in which one of these lone pairs is this one, the other one is this one here. I've just shown it like this one. And for simplicity case, I've just done what? This is the other end of the lone pair, of this p orbital. So this is the p orbital containing the electrons, which wants to bond with the hydrogen here. Now, this bond here, I'm illustrating as this covalent bond here, whereby hydrogen is a sphere. Hydrogen bonds with the s orbital. All the other atoms they usually bond with the p orbital. We're talking about electronegative elements like halogens, like bromine, fluorine, things like the oxygen, and even carbon. It usually bonds with the yeah with the p orbital. So we're just going to show you a p orbital. In this case, this bond here. So there is this bond here it is the p orbital for the bromine. It's overlapping with the s for the for the hydrogen. Can you see that? So this is what happens at the microscopic level. So the oxygen has got to approach the hydrogen along that plane. This is what happens. So if the approach is not possible, let's say because of steric hindrance, then that reaction is not going to take place. Even if the orbitals may appear exposed. So the thing is, if you're going to be showing with the orbitals, it can show some issues which may not be possible by just showing the curly arrow. So let us see here. So this orbital for the oxygen is going to be approaching the the sphere for the hydrogen along this axis here. And when you're dealing with the SN1, SN2, you're just being shown like a transition state. So in the transition state is where you've got the partial bond which are forming and those which are breaking. So at that point here, the orbital for the oxygen will just be touching the one for the hydrogen here, and then so this is the developing bond between oxygen and the hydrogen, and this is the breaking bond between hydrogen and the bromine here. So at the end of it, this hydrogen is going to be fully bound to the oxygen. So there will be a full covalent bond between oxygen and your hydrogen. And then this bond between your hydrogen and your bromine is going to break. And then those electrons between your hydrogen and your bromine will go to the bromine to become your new lone pair. Can you see now? Yeah. So this is what you're going to be showing us here as your bromine here. Now this structure may not be easy to understand, but showing the orbitals here, it's quite easy to show here how the oxygen approaches, takes up the, overlaps with the hydrogen, the sphere for the hydrogen, pulls the hydrogen to itself, forms a covalent bond between the oxygen and the hydrogen, and then the bond between the hydrogen and the bromine breaks, and then the bromine moves away. So this is the same as what you're showing here. Now the oxygen has now used its lone pair to form the bond here. So as a result of that one, it's going to be deficient because it's used up its electron. It was initially neutral, so it will end up being positive charge. So that you are going to show. So this is the structure of the of the orbital here. So the thing is, so this oxygen is going to be what? It's going to be positively charged. It's going to have three bonds here. So um, so this is your illustration of your uh, so this is the illustration of this Kali arrow mechanism. Now, so by combining both the Kali arrow and this orbital illustration, then I think you can really be able to see how the reaction is going to take place. So I'm just going to pause a bit, and then we'll see one example involving formation of a double bond to show how exactly the double bond is going to be forming. One involving the Kali arrow, and then the other one involving the yeah the yeah the yeah this uh, molecular orbitals. I hope you are enjoying this session of showing both the Kali arrow and the orbitals. Okay, so I'm just going to pause, and then I'll put the next thing on the board. Yeah, all right. Okay. Okay, class. I don't know whether it will be visible. I can see. Um, I'm just trying to put. Uh, there's the Yeah, I think the one at the bottom is now being seen. It was not being seen well, okay? So there is this example here. Uh, so this one, can you see well? This an R is an alkyl. So this is an alkoxide, oxygen. So this is an anion, an alkoxide. Oxygen has got three lone pairs. It means it is negatively charged. So there are the three lone pairs. You say this is how you usually show the mechanism. The Kali arrow starts from the lone pair on the oxygen, attacks the hydrogen, and then the electrons come to between your carbon and carbon here. As a result of that one, then the bond between your carbon and chlorine falls off to give now. It means that your oxygen will have abstracted your hydrogen, and then you say you're forming a double bond, and then your chlorine falls off. Can you see that? Let me repeat again, yeah? So you've got your alkoxide, it's the base, it's abstracting the hydrogen, and so you've got an R group here, you've got your hydrogen. These ones are not part of the reaction. And then please note this, yeah, that if you're going to show a bond here, say that you're forming a bond between your oxygen and the hydrogen. So hydrogen forms one bond. So if you're going to form a bond between your oxygen and the hydrogen, then the bond between your hydrogen and the carbon will have to break. So those electrons are going to come between your carbon and carbon here to become your double bond. Now, now this bond has already broken. So this carbon is going to have 1, 2, 3, 4. So this carbon, as a result of this double bond, is going to have 1, 2, 3, 4, 5. So one of the bonds will have to break, and the one which will be breaking is the one for the good living group, which will be the halogen. In this case is the chlorine. So the electrons are going to end up on the chlorine, and you'll end up with each of the carbon atoms having 4 bonds. Now, let's look at the same thing using the molecular orbital illustration. I think it can be seen very well here. So this structure here, I'm I'm just choosing one of the lone pairs. I say the lone pairs of the oxygen are based on the p orbital. So I'm going to say I'm just choosing one of the p orbitals. I've put your my lone pair, and then I've put my p orbital. It wants to form a bond with your hydrogen, which is a sphere, and that hydrogen is attached to your carbon as a p orbital. Can you see here? So there is this hybrid orbital of the carbon. It is overlapping. Let me show it correctly that is actually overlapping correctly. Yeah. So this is your hydrogen. Yeah. So it's a full bond here. Carbon, uh, uh, carbon, hydrogen bond. So this p orbital wants to overlap with your hydrogen. And then in the transition state, this is how it's showing here. The oxygen here is now overlapping with your hydrogen here. And so this you're developing oxygen hydrogen bond in the transition state. And then there is the bond between your carbon and hydrogen uh, and the and the carbon here. That bond is almost breaking here. And then can you see this? This orbital is still there, and then the one between your carbon and chlorine bond is still there. Yeah, is still being there. So as a result of this hydrogen being being pulled there, can you see in this illustration here? So the bond between your carbon and the hydrogen is going to break. So this hydrogen, this pair for the hydrogen s orbital is going to be joined to the oxygen here. Can you see here? Now you're going to be left with your orbital there. Now the hydrogen went off without electrons. So those electrons are going to be left on this orbital which has been left here, and then the bond between your carbon and chlorine bond. Can you see this bond is going to break? Is going to detach. So this chlorine is going to go with your two electrons. But the two electrons which are there between your oxygen and the hydrogen are going to be in these two orbitals, which will now form your new pi bond. So your new pi bond, this pi bond is now this orbital here. Can you see now? So this is now your pi bond, which is now your pi bond here. Now in this case, your chlorine has now gone off. So I hope you can be able to see from this illustration of the orbitals how it illustrates how the mechanism is going to take place. Sometimes you can look at the mechanism and say, hey, how does this curly arrow come in and here? But if you're going to combine with the flow of the orbitals, you're just going to see it will not be hard knowing exactly how you're going to put the curly arrow. Yeah. So the most important thing here, which I want you to see, is how uh, the 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 sigma bond between your carbon and the hydrogen, and also the sigma bond between your carbon and the chlorine bond, the ones which have been left as a result of the chlorine going off and the hydrogen going off, now become your new pi bond. Yeah, that one is very clear in this illustration of the orbitals, which is what you're going to be using. You're going to be using these orbitals plus the curly arrow to really show how the mechanisms are going to be taking place. I hope you are really enjoying this this illustration to show how the curly arrow and also with this orbital illustration. So the next one which you're going to be looking at later will be where we'll be having uh, maybe something like a nucleophile coming into a carbonyl group. So that one you're going to be looking at later. So I really hope you're enjoying this illustration of both the curly arrow and showing the orbitals interaction. In this case, there is no guesswork. In this case, you're just going to see how this one is actually joining here, this one is detaching, this one is detaching, this one is moving on to give the rest. Yeah, this one is very, very easy. as opposed to here just showing the arrow here coming here and here. So, but if you're going to combine this with this, then you're going to see how the mechanism are going to really flow. So you just need to stop there before I give you another example. Thank you. Okay.